10.3 is about identifying different types of models and how we can recognize those. And we're going to focus on 3 main types of models: linear models, quadratic models, and exponential models. And we're going to talk about how do we identify these from a table, from a set of ordered pairs, or from a graph. So let's look a little bit more in depth on each of these 3 models, because these 3 models are really commonly used in the business world. You'll see things like this when you're analyzing different kinds of data. Depending on where your path takes you, this is the type of thing you will see. So linear is probably the one that you're the most familiar and comfortable with, because we spent most of first semester talking about a linear equation. So we learned this first semester. And linear functions are functions that have an x value or an x and y value if it's not written in function notation. Here we see slope-intercept form, or f of x, and I'm not sure why this got cut off, but f of x equals notation, function notation, or y equals notation. We could also have it in standard form or point slope form, but the key thing is that you see an x value and a y value. When we think about a line or a linear function graphically, we know that we're going to see the graph of a line. It could also be a horizontal line or a vertical line, but we're talking about a linear function. And the thing that's wonderful about linear functions is that they have a common slope, right? They move in a particular way. We have a rise over a run. And in our graph, we know we can count that rise over the run. But in a table, the way that you can see that rise over the run being constant is with the first difference. So you'll notice that all of these x values are just increasing by 1. So our x's are changing in the same way. And what's happening with the y values? To get from 1 to 3, we add 2. From 3 to 5, we add 2. From 5 to 7, we add 2. From 7 to 9, we add 2. And all of these plus 2's, this is called the first difference, because it's the first time that we have looked at how we behave or how we get from one y to the next y. And you can think about this in terms of slope. Another thing that you can think about is we just spent some time talking about, well, what happens if we have this common difference? We called that arithmetic. So you can also think about a linear model in the same way that you think about an arithmetic model, because an arithmetic model is linear. So if we're looking at an equation, we're looking for x or y, no exponents. If we're looking at a graph, we're looking for the graph of a linear function. If we're looking at a table, we're analyzing those first differences and seeing if those y values are changing by a common difference, or if we would recognize it as an arithmetic pattern. When we think about quadratics, which is what we just spent all of Unit 9 covering, we know that a quadratic, the key thing about a quadratic is that it's a second degree function. That's what makes it a quadratic. Again, we can have y equals or function notation either way, but we know a lot about quadratics based on Unit 9. We know that the shape of the graph is a U-shaped, facing up or opening upward or downward. Yes, there are sideways opening parabolas, but we have not covered those. In this course, we will save that for your future courses. What we haven't talked about before is how could you recognize that a model or a function is quadratic if you were just looking at a table of values. So the first thing that you would do is, just like we did with looking at the linear table, you would look at the first differences. So these right here are the first differences, and you would notice that they are not the same. How I get from one y value to the next y value is not with a common difference. Then you would say, well, how do I get from these first differences to the next one? So you're going to look at what we call the second difference. And if those are the same, if those second differences are the same, then we can say that the table of values is modeling a quadratic function. And then last but not least, the first thing that's really new in this section, that's not true. This that we just talked about was new. But the first new type of function or the new type of model is an exponential model. And that's what we're going to spend a lot of the rest of this unit talking about, is modeling exponentially. So let's get a little bit of information about an exponential function. It is of the form y equals a times b to the power of x. And just like with a line, a and b are going to be some value, just like b is a number when we see it in slope-intercept form. A and b are some values. A is not allowed to be 0 and b is not allowed to be 1, because if either of those two things were true, we wouldn't actually have an exponential function. And our b value must be greater than 0. So here's a couple of examples. Y equals 2 times 4 to the power of x, or f of x equals 2 times 4 to the power of x. That's an example of an exponential function. If we're looking at an exponential function graphically, it sort of looks like we're creating a ski slope or a ramp for skateboarding. So it has a curve to it that is really unique. Another thing that's really unique that we'll focus on in 10.4 is that every exponential function has what we call an asymptote. And an asymptote, let me write that word out here, is a line that the graph never crosses. A line that the graph never crosses. And in this class, we're pretty much always going to be looking at exponential functions that have an asymptote at the line y equals 0. And we'll talk about why when we get to 10.4. But so they sort of have this upward curving shape or downward curving shape that's very distinct. And at one end, they're going off to infinity, and at the other end, they're getting closer and closer and closer to the x-axis. What does that look like in a table? Instead of looking at the common difference, we're going to actually see that there's a common ratio. We're multiplying by some constant value to get from one y value to the next. And this should sound a little bit familiar. This sounds a lot like a geometric sequence, which we talked about in 10.2. So these are the three types of models that we are going to become familiar with: a linear model, a quadratic model, and an exponential model. And the key thing in this section, our essential question, are what are the different types of models? We just identified the three different types of models we're going to be discussing. But more importantly, how can we recognize them? So what we're going to do now is we're actually just going to look at 4 examples. We're going to identify the type of model for each of those examples, and then that's going to be it. All right, example 1, determine the best model and explain how we know. So we have time and the number of bacteria. So time is pretty much always our x value. Bacteria is going to be our y value. Our x values are all increasing by 1. So what we're going to do is figure out how do we get from one y value to the next. So the first thing I would probably check is what number am I adding to get from the first value to the next? So if I do 96 minus 24, that's going to give me plus 72. 384 minus 96, what do I add to 96 to get 384? I add 288. So I can already tell that this is not going to be an arithmetic sequence because these two numbers are not the same. And not going to be a linear model because the common difference isn't the same. The first difference isn't the same, so this is not going to be linear. The next thing I'm going to check are the second differences, but let's go ahead and fill the rest of this in. Here I'm adding 1,152. And here I'm adding 6,144 minus 1,536 is 4,608. So it's not linear because the first differences are not the same. Let's go ahead and look at the second differences. To get from 72 to 288, I am adding 216. Now, I can already tell that I'm not going to be adding 200. I'm going to be adding a lot more than 216 to get from 288 to 1,152. So it's also not quadratic. And I'm not going to keep checking these numbers as soon as I know, which means we're only left with one type of model, and that is our exponential. But let's check and see. How do I get from 24 to 96? Well, let's look at what happens if I divide 96 by 24. That's going to give me 4. So let's check and see, does this work? If I multiply by 4, what's 96 times 4? 96 times 4 is 384. That works. 384 times 4 is 1,536. And obviously it's okay if you're checking on a calculator for these numbers. If I take 1,536 times 4, I get 6,144. So all of these numbers are the same, which means the answer to number 1 is that this is an exponential model since we're multiplying by a common ratio. In this case, that ratio is 4. Okay, number 2. Why don't you go ahead and pause the video and look at how you get from one y value to the next y value and see if you can identify those first differences first. So hopefully you've had some time to look over that. To get from -14 to -9, we're adding 5. From -9 to -4, we're adding 4. Remember, we're simply looking at these y values here since the x values are changing constantly. To get from -4 to +1, we're adding 5. And to get from 1 to 6, we're adding 5. These are all the same, which means this is a linear model since our first differences are the same, or since we have a common first difference. Okay, number 3, which is not numbered down here, so I'm going to call it number 3. Again, we're going to look at first differences. To get from 4 to 68, we're going to add 64. To get from 68 to 100, we're going to add 32. To get from 100 to 100, we're going to add 0. And to get from 100 to 68, we're going to subtract 32. So right now, we know this is not linear because these are not all the same number. Go ahead and pause the video and look at the second difference to see if it's quadratic. Okay, hopefully you've had some time to pause the video. We're going to look now at the second difference. To get from 64 to 32, we subtract 32. To get from 32 to 0, we subtract 32. To get from 0 to -32, we subtract 32. So our second differences are the same, which makes this a quadratic model, since our second differences are the same. The last one here, number 4, is giving you a graph and asking you what type of model this is. Well, this is an exponential model. Again, it's approaching that x-axis but never crossing it. So we can tell just from the graph that this is exponential. Now that's the last example in the notes, but I'm going to just add one thing on here, one quick end of the section check, and see how you do. All right, we definitely saw an example of each of the tables, and we had pictures of each of the graphs. So I think that you can start feeling comfortable identifying, looking at a graph, since you have a picture of a sample of each of those graphs, and from a table, since we did 3 examples. But what I wanted to do just really quickly, and let's make this multiple choice, is have you match up each of these equations. Is it linear? Is it quadratic? Or is it exponential? To see if you can identify it from an equation, since we didn't really do that yet. And you could look back at your notes to see this as well, but go ahead and pause the video and just take 2 minutes, see if you can put A, B, or C, A, B, and C in whatever order they go in here. Okay, hopefully you have had enough time to pause the video. This first one is linear. I can tell it's linear because there's an X, there's a Y, there's no squared signs. X is not in the exponent as it would be for exponential, which is what I am seeing in number 2. Number 2 would be C, exponential, because the variable is my exponent. Variable is the exponent, which by process of elimination leaves us with number 3 being B, but we can also tell that because it is squared, or a better way to say this, it is a degree 2 function. So key things from this section, the 3 different types of models, linear, quadratic, and exponential, being able to identify them if you're given an equation, if you're given a graph, or if you're given a table or list of ordered pairs. Remembering that what they look like, a line looking like a line, a quadratic looking like a U-shaped or an upside down U-shaped, and an exponential looking sort of like a slope. And when I say slope, I'm thinking skateboarding or snowboarding. And then given a table or a list of ordered pairs, looking at those first differences for linear, looking at those second differences for quadratic, and analyzing if we're multiplying to get from one y value to the next for exponential. So write down any questions you have, and I look forward to supporting you on this in class. Thanks for listening.